There's a few motion curves that we would like to have a look at and look at their properties. Well, okay, guys, just submitted during the break, so we need to get started here. Okay. So, a straight line. Well, a straight line having an initial point at the point x naught, y naught, z naught, and having a direction vector a, b, c. All right. So, well, we know how to get the parametric equations of a line containing 2 points, or rather an initial point and what's that? And a direction point. Well, so we use the initial point and the components of the direction vector that are what the coefficients of the variable t in our vector valued functions. Well, so that's going to give us the position vector. Recall that a given function gives the position vector, the derivative gives us the velocity, and the acceleration gives us the second. It's given by the second derivative. All right. So, okay, so if we take the derivative, well, this is constant, that's going to go to 0. The derivative of t in the vector valued function is 1 times whatever multiplies the t, which in this case it's the direction vector. So that's why for the velocity we get the direction vector. And the acceleration is 0 because here we would be differentiating a constant vector. So the derivative of a constant is 0. We're taking the derivative of 3 constants a, b, and c. And well, another very important trajectory, which is the circular trajectory, that is typically parameterized with a cosine in the x component and a sine in the y component. That's what we got back in parametric equations in calculus 2, at the end of calculus 2. In this course, we just make it a vector valued function. We change the notation to a vector valued function. So, well, so number one, let me do the graph for this. Let me do a very generic graph. And okay, so that's going to be our circular trajectory. Also, well, very oftentimes the most common case is to direct this circle in the counterclockwise direction. Typically, that is the positive orientation of the graph, right? So, and actually, well, that makes sense when we connect this with how we generate our trigonometric functions back in pre-calc, you know, because the angles increase in this direction rather than clockwise. Well, so the cosine relates to the x component, the y relates to the sine component. So let's indicate the orientation first, all right? Let's indicate the orientation. So, a cosine t, a sine t. This a is going to represent the radius of the circle we're having a particle traveling along. So it could be a unit circle, a equals 1. Could be any radii, 5, 7, 9, your favorite number. Well, so let's have a look at the derivative. Well, before taking the derivative again, these points on the unit circle will be, okay, these points will be the terminal points of vectors in standard position. So let me label this as R of t, all right? Because then we will also graph the velocity vectors and the acceleration vectors. Now, let's find the derivative of this vector valued function. Derivative of cosine, negative sine, derivative of sine, positive cosine. Well, so now where are we going to graph the velocity vector? Well, so recall that the derivative of a vector valued function gives us what? The tangent vector. So that means we're going to go to this point and draw a tangent vector. Now the question is, in which direction should we write that tangent vector? Notice in this case the direction of the circle, of the trajectory. So that's the direction in which the velocity vector has to point. Also, the signs of the components of the vector valued function would give us an idea how to plot. That means we need to go negative in the x direction and positive in the y direction. So at any point I need to go negative in the x direction, positive in the y direction, giving us this vector as a result. All right? So that is our velocity vector labeled v of t. All right? So that's the first derivative. What about the acceleration vector? So at this point, at this same point, we should plot this vector. Well, in which direction should we go? Well, notice the signs of the component. So we should go negative, negative. That means I need to go negative, negative. Actually, kind of going back to, use a different color, kind of coming back to the origin, if you will. All right? So, and actually, that's something we're going to see about later. The acceleration always points in the direction of the concave side of the curve, not the other side. All right? And the velocity always goes in the direction of increasing time. That's something we discussed last time. So here we can answer a couple of questions. So what is the relationship between the position vector and the velocity vector? Any ideas? Look at the position and the velocity. Yes.
Is it a right angle?
There's a right angle. So more formally, yes, that's right. There's a more formal word for that. They're orthogonal, right? All right, they're orthogonal. What about the position and the acceleration? They're parallel, right? Even though they go in opposite directions, that's fine, but they're parallel. All right, so that means, well, that the motion on a circle or potentially in a sphere, which is the 3D version of the circle, if we will, that has a constant radius, because otherwise if it has a different radius, it is not constant. Well, that will be a different shape. Well, that means the position dotted with the velocity. What is that going to tell us about it? That equals to what? So when two vectors are orthogonal, 0, right? Is that 0 or the 0 vector, first of all? Just a 0, right? Because dot product outputs a scalar, not a vector. All right, let's see a little bit of this in action, actually, with a curve in space. Well, so we have this curve moving on a trajectory described by r of t equals to 4 sine t, 5 cosine t, and 3 sine t. So we need to show that the object moves on a sphere. How are we going to do that? Okay, so let's take the magnitude. So, well, you might ask yourselves, why are we going to take the magnitude? Well, you'll see. So let's take the magnitude of r. That equals the square root of the components 4 sine t squared plus 5 cosine t squared plus 3 sine t squared. All right, what's that going to give us? Well, that's going to give us a 16 sine squared t plus 25 cosine squared t plus 9 sine squared t. All right. Well, so combining like terms, what's that? The sines, that's 16 plus 9, that's 25. Sine squared t plus 25 cosine squared t. Well, we can factor out a 25. That's going to leave us with a sine squared t plus cosine squared t. That equals, okay, isn't that an identity? That equals to 1. So that equals 1. And that's the square root of 25 times 1, which is 1. That equals to 5. Well, actually, this is just good enough to show that this object is moving on a sphere. Well, how? Because, well, let's recall the equation of a sphere. The equation of a sphere in its generic form, if you will, that is given by x squared plus y squared plus z squared equals to r squared. If we take the square root on both sides to solve for r, that's the square root of x squared plus y squared plus z squared. That is, we're getting r, that is a number, not a variable. Like in this case, we're getting a constant that looks like an s, should be a 5. So with this, we show that this is traveling along a sphere because we end up having a constant radius, so to speak. All right, so they're asking us to find the velocity and the speed of the object. In this case, careful, because velocity and speed, it's not the same. While velocity, it's a vector, the speed is the magnitude of the velocity. So let's find the velocity, that is v of t, which is the square root, not the square root yet. So that is the derivative, that is 4 sine t, 4 cosine t, negative 5 sine t, and 3 cosine t. Okay, so now we need to find the magnitude of the velocity, that is the speed. That is 4 cosine t squared plus negative 5 sine t squared plus 3 cosine t quantity squared. All right. So that means what's that going to give us? Well, a very similar result, that is 16 cosine t quantity squared plus 25 sine t quantity squared plus 9 cosine squared t. Okay. And again, combining like terms, the cosines in this case, 16 plus 9, that equals to 25 cosine squared t plus 25 sine squared t. And what's that? Again, we can factor out the 25, and that's going to leave us with the identity we just simplified earlier, which is square root of 25, because again, this is equal to 1, and the square root of 25, equals to 5. So the speed is 5. It's the same as the radius. Well, that's because, okay, just think about it. We're on a sphere, so where its curvature, it's exactly the same. So the speed has to be exactly the same at every single point. Well, about curvature, we're going to look at it in the next section. No, in the next couple of sections, not the next one. All right, so that's an example of looking at particles over a trajectory, or an object over a trajectory. Then in the next topic, let's have a look at projectile motion. All right, so as I mentioned in the previous class, we were going to derive a model. Well, I mean, the formula you already know from physics. You may see it with a different notation or the like, but essentially it's going to give us the exact same result. All right, so okay. So if we consider the two-dimensional projectile motion, where the only force acting on the object is gravity, of course there's other forces that may interfere in the projectile motion, like temperature, maybe pressure, and many other things. But for this situation, we're going to ignore all that. All right. So g represents the acceleration due to gravity, on Earth, of course, unless you're on a different planet. Well, you can deduce the same or derive the same equation, just change the gravity, the acceleration due to gravity for whatever planet you want to look at this. Okay, so g in general, it's either the 9.81 meters per second squared or 32 feet per second squared. All right? Okay. So now let's assume that the object has an initial velocity, that is at t equals to 0, that is v of 0, which has components u0 and v0, and an initial position of r of 0, which is x0, y0. Recall that we use v for velocity, r for position, or every time you see subscript with zeros, that means or represent initial values. In this case, initial velocity and initial position. So again, in a similar way, we already solved a problem like this actually with numbers. Now we're going to do it with symbols to get a generalized version of this equation or of this vector value function. Okay, so if we start by writing the acceleration vector, well, we're going to go acceleration integrated to get velocity, integrated again to get the position, the same way we did it yesterday. All right, how would you express the acceleration vector, number one? Any ideas? That's going to be our starting point.
0 and then negative 9.8.
And negative 9.0. Well, let's do 0 and negative, let me call it negative g, all right? Because depending on the situation, because we're generalizing this, and depending on the situation, we may use the meters per second square or the feet per second square. So that will depend on depend on the context of a particular situation. But in general, okay, so we're going to let's do this. Okay, so to go from acceleration to velocity, then we need to, okay, velocity, that's the integral of the acceleration with respect t, or with respect time. That is the integral of 0 negative g dt, which is, again, the integral of 0 is 0 plus the constant. In this case, I would like to call this c1, plus the integral of negative g. This is constant with respect t. That's negative, comma. That's negative gt, plus, let me call this c2. Okay? So now we need to use the initial condition, that is to find the constant c1 and c2. Which initial condition are we going to use? Well, that of the velocity, because we're trying to find the velocity expression. And then we're going to repeat the process to find the position. Okay? All right. So we know v of 0. Okay, let's let that equal to c1 comma negative g times 0 plus c2. That's going to give us, on the right hand side, keep the c1 comma c2, but on the left hand side, v of 0, that equals to the vector u0 v0. Okay, so that's what it's equal to. And then again, two vectors are equal if their components are equal, right? So set components equal to each other. u0 equals to c1, v0 equals to c2. So c1 equals u0, c2 equals to v0. So now we're good to go and write our velocity expression, or our velocity function. That is u0 comma negative gt plus v0. At least the y component of this vector value function looks familiar from your physics class, right? So this is where it's coming from. Maybe you were just given those equations. Maybe your physics was a calculus-based physics and you did something like this. If not, well, this is where it's coming from. Now, let's do a second iteration of the same problem. That is to go from the velocity to the position function. So position, which is r of t, that equals the integral of the velocity with respect to t, which is the integral of the function we have at the top here. So that is u0 negative dt plus v0 dt. All right. So let's integrate this. So the integral of u0 dt, that is going to give us, okay, r, so u0 t, plus, okay, in this case we already used the letter c, c1, c2 to go between the acceleration and the velocity. Let's use a different letter. Let's use k1. Let's use k. And then the integral of negative gt, that is negative 1/2 g t squared plus v0 t plus k2. I know what you might be thinking here. So should we do the absorption process of to multiply the 1/2 with the constant? Well, not at this point. So save that to when you apply this to a given situation, right? Okay, so let's do the same. Let's use the initial condition to find the constants k1 and k2. How are we going to do that? Using the position vector, the initial condition for the position vector. So again, I'm going to set, no, it's not V, it's R of 0 equals to, I'm going to substitute this u0 times 0 plus k1, comma, negative 1/2 g times 0 squared plus v0 times 0 plus k2. And simplifying all this, that's going to give us, okay, 0 plus k1, that's k1. And then 0, 0, k2. And that equals to the initial position vector, x0, y0. And again, two vectors are equal if their components are equal, right? So that means we can equate components. K1 equals to x0. And k2 equals to y0. Alright, that means R of t finally is u0 t plus x0, comma, negative 1/2 gt squared plus v0 t plus y0. Does that equation look familiar from physics? It's the same. Maybe you didn't write it with this angular parentheses or brackets. Maybe you didn't write it with this notation, but this is the exact same notation as the projectile motion. Also, it's the free fall, right? The free fall equation with a different letter rather than having the v. It has all y's, I believe, right? But somehow they're the same. Well, the best would be to see this formula in action. Of course, you're not asked to memorize this derivation. So I usually like doing this derivation proof so you can see where things come from, just instead of just giving you, oh, here's the formula. Let's just memorize and use it. So this actually puts together what we have learned about integration of vector valued functions, initial value problems, or finding the constants of integration. So put together to solve a physics problem, essentially. All right. Let's have a look at a couple of examples. Okay, so suppose a baseball is hit across a flat field from an initial position of 2.5 feet above the ground with an initial velocity vector. Oh, okay, we're giving a vector, we're giving scalars, we're giving a bunch of information. Letter A, they're asking for the velocity and position vectors, and they're asking us how far does the baseball travel horizontally before it hits the ground, and when does it hit the ground. So, okay. So, because this is a vector valued function, we need vectors. We're given the initial velocity as a vector, but somehow they're just giving us a scalar as the initial position. We need to turn that into a vector. Well, they're telling us that the initial position is 2.5 feet above the ground. So we need to represent that using a vector. So let's write the vector that is R of 0. So how would you represent the height of the initial height of the baseball using vector? Because this is a scalar only. How would you represent it? Any ideas? 0, 2.5, right? Because it's 0 units in the x direction, and it's just displaced 2.5 in the y direction. Okay? Well, the second vector, that's the initial velocity, that equals 25, 4. It's just given like this, all right? Okay, so let's write down our position function R of t based on what we obtained previously. That is, okay, u0, so this is going to be, let's label. How about that? Let's label. This is our x0, y0, u naught and v naught, right? Just so we can simply substitute in the equation. So u naught, that is 25t plus x naught, which is just 0, right? That's just 0, comma, negative 1/2. G, in this case, well, actually, what G should we use? 9.81 or 32? 32, because we're given feet, right? So that times 32, and t squared, and what else? Plus v naught, which is 4t plus v, oh wait, yes, that's a v naught, yes, y naught, which is 2.5. So that is our position vector. You might want to simplify this again, okay? That is 25t, comma, negative 16t squared plus 4t plus 2.5. So that is our position vector. So that's going to give us the position at every single value of t. All right? Okay, let's find the velocity, that is the derivative of this vector valued function. That is the derivative of 25t, which is 25, the derivative that is negative 32t plus 4. So that is our velocity vector. All right? Now the question is, part B, how far does the ball travel horizontally before it hits the ground? Well, we're going to use our graphing calculator here, so get it ready. So number one, let's draw a diagram. Okay, a diagram would be great. So all right. Well, let's see if this, whoops. Let's see if this works. It's not going to work. Well, somehow. So here what do we have? We have the baseball being hit at an initial height of 2.5. All right? They're asking us how far is it going to hit the ground, and also when it's going to hit the ground. Okay, so how far when it hits the ground? Well, so in this case, okay, any ideas how would you do this? Yes.
The y component equals 0.
Let's set the y component equal to 0 because it's about the height. It's a y component that gives you the displacement in the y direction, which means height. All right. That is set negative 16t squared plus 4t plus 2.5. Let that equal to 0. And well, although you have alternatives to solve this equation, well, I wouldn't recommend factoring. I don't think this is going to be factorable because now look at the decimal. You don't want to work with decimals. And even though you could use the quadratic formula, that's acceptable as well. It's going to take you forever. In this case, just use the graphing calculator. But when you solve a problem like this on the homework, be careful about the amount of decimal places to put on your final answer, right? So my advice, always save about 3 or 4 decimal places. So in my notes, I have this as with 4 decimal places. So let's see. Let me go to the graphing calculator. I said I open it. Okay, so let's see, y, okay, make sure it's in the correct mode. Let's go back to the function mode and type the equation. So that is negative 16t squared, well, I mean x, it's still the same, plus 4t or x, and plus 2.5. Well, so you want to know, okay, let's graph this. So I would like to zoom in here, that's fine. Okay, so I would like to find the x-intercept. So the x-intercept, that's going to give us, well, first of all, actually the way the question is worded, it's in a way it's backwards. First we get to find out when. So that is the x-intercept, which is going to give us the t at which the height equals to 0. So to do that, go second, trace, and find the 0. So notice how we get this star flashing. So click enter at any point before the intersection and click enter at any point after the intersection. That when you get the calculator to find an intersection in between those two values. So, and click enter again. And we get 0.53957. Okay, I'm going to round to 4 decimal places for now. All right, so let me go back to the notes. So this is for t approximately 0.5396 seconds. Okay, here's where we need to put units. So yeah, pretty quick. Now, barely half a second. All right. Now the question here is, well, how far does it go? Well, how would we find how far does it go? Any ideas? Hmm? In 25t, right? In the x component, because the x component of the vector value function indicates the displacement in the x direction. That is the how far, not the how high, like for the first part of the problem. So evaluate x of 0.5396. Only the x. Notice I'm just using x, not the entire vector value function. That is equal to 25 times that number, 0.5396, which is approximately 13.49 feet. All right. So this is very formulaic and mostly calculator, so there's nothing, I mean, maybe the trickiest part of a problem like this is that the position was given as a scalar, but we need to make sure we get everything in vector form because these are vector value functions, all right? So, okay. Let's have a look at the next and last part of the section, then we move on to 14.4. Okay, so this same situation can be remodeled, you know. But what if in this case we only know the initial velocity and the angle at which a rocket is being launched or a baseball is being hit. All right, so modifying this equation using trigonometry gives us as a result this equation right here in vector form, where x is the I component is the x displacement and the y component is the y displacement. I mean, it works the same way. It's just the way this equation is presented. So let's have a look at one example to see this formula in action. Number one. A baseball is hit from a height of 2.5 feet. Very similar situation. What else? With an initial velocity of 140 feet per second and at an angle of 22 degrees above the horizontal. So be careful when setting up the vector value function for this. Make sure your calculator is in the correct mode. It's in this case in degree mode. Unless you're given radian mode, well, use the radians. But in this case, the minute you see this degree symbol, make sure your calculator is in the correct mode. Okay, so write the vector valued function representing the path of the baseball. Okay, so number one, R of t equals v naught, that is the initial velocity. Notice the velocity this time is not given as a vector, but rather as a scalar, because it's going to count for both components in the equation, in the form or in the function rather. So that is, what's that? 140. Notice the parentheses, you'll see y. Cosine of the angle, in this case 22 degrees. That's because this number right here, it's only the coefficient of the variable t. Right? Also, okay, so that's the x component, comma. Okay, h, that's the initial height, which is 2.5 feet. and then plus v naught sine t, that is again parentheses v naught 140 sine 22 degrees times t minus 1/2 g, which in this case is, since in this case we're using feet, that's going to be again 32, and t squared. All right. Well, how about we just do 16? I mean, I think we can simplify this one on the go. All right. So that is our vector valued function. I mean, in the exact form, without computing the sine 22 degrees times 140. We're going to do that later. Don't worry. All right. So that is the vector valued function that represents the path of the baseball in its trigonometric form, because we're given angle this time and initial velocity not as a vector. All right. Okay. What is the maximum height reached by the ball in this case? Any ideas? How do we get that maximum height?
Velocity equals 0.
When the velocity equals 0, but here we need to be very specific about which component of the velocity, because we have the horizontal component and the vertical component. So the vertical component, right? So that is when the vertical component of the velocity equals 0. That means we need to take the derivative of this vector valued function. Okay, so let's do that in the same part A. We're going to use it in B. So that is v of t, that equals, okay, the derivative of t is 1 times its coefficient, that's just the coefficient, 140 cosine of 22 degrees, comma, the derivative of 2.5, that's 0, the derivative of t is 1 times the coefficient equals the coefficient, 140 sine 22 degrees, and minus 16 times 2, that's minus 32t. All right? So this means for part B, we need to set only this y component equal to 0. That's going to give us the time where the time when the ball is going to reach its maximum height. Right? Well, they're asking us for the maximum height, but we need to find out when first before getting that height, right? So that means we're going to set 140 sine 22 degrees minus 32 equals to 0. That is, let me point it out here. And let me solve this linear equation. That reduced to a baby linear equation equals to negative 140 sine 22 degrees, and divide both sides by 32 to get t equals, first of all, 140 sine 22 degrees divided by 32. And then t would be approximately 1.639 seconds. Right? Yeah, I know that the what's it called, the units per second, it's not, in general we can write it as sec like this, but it's just s, but I'm using the word just so I don't confuse an s with a 5 or something. Okay? All right, so well, that's only when it's going to reach the maximum height. How do we get that maximum height this time? In the y component only, right? We don't need the entire, we don't need both components, just the y component. That is, then go like this: y evaluated at 1.639, that equals 2.5 plus 140 sine 22 degrees times the time, which is 1.639, what we just found in the previous part, and then minus 16 times 1.639 quantity squared. And after simplifying all this madness here, you should get 45.476 feet. And in this case, I'm using 3 decimal places. Again, when you solve a problem like this on the homework or on the exam, for instance, just make sure to consider the correct amount of decimal places, so you don't get it wrong and you don't input your answers on my MATLAB and having to do it 17 times because you're not rounding correct. And by the way, notice how this is essentially a two-step part of a problem. Recall, as you would do in a physics or mostly in a chemistry class, do not round until the very end. All right, do not round until the very end, because even though here I'm not looking for significant figures or the like, well, think of think that you're doing with these significant figures as in chemistry. So just because, again, my MATLAB may be a little picky with the rounding, with the tolerance, so just so you keep it in mind. All right. Use your graphing calculator to graph the path of the ball and determine whether it will clear a 10-foot high fence located 375 feet from the plate. All right. So the picture here is so we have this, and there is a fence right here. All right. And what's going to happen here? Well, so the question here is the ball going to make it through the fence, or is the ball going to hit the fence? We don't know. It's either one or the other. We'll find out. Right? We'll use our model here, our graphing calculator, to determine that, and also a couple of calculations. All right. Now here is the issue when it comes to using our graphing calculator, because if you type this equation, right? If you type this equation that in parametric form, of course we're going to go back to parametric form. You may not get the right graph. Well, not the incorrect graph, but I mean a good window of the let me change mode of the trajectory here. So let's see. So I'm gonna change from function to parametric again, and let me type the function we have right here. Okay, so x1t, that's going to be our x component, that is 140 cosine of 22 degrees. Close the parentheses for the 22 and multiply by t. All right. And then the y component, that's 2.5 plus parentheses 140 sine 22 degrees, and that's plus, right, or rather minus 16 t squared. Okay, so if I click on graph right here, I'm not even going to be able to see the graph, because think about it, we have like really big numbers such as what's that, 140, 2.5. What do I have here? 1, 2, not even the 2.5. Well, so here I have the window settings. Okay, let me write it down on the paper. I mean on the notes. Window. So make sure your t goes between 0 and 5. Because I already done this a few times, so I know what window works for this. Then do from 0 to 400 for x, and 0 to 50 for the y. All right? Okay, what do I mean by this? Okay, let's go back to the calculator, go to window, and that's the Tmin, Tmax, Xmin, Xmax, and Ymin and Ymax. So from 0 to, what was that? 5, right? 0 to 5. And then the t-step, well, 0.01, that's fine. And Xmin 0 to 400. And Ymin, again, another 0, and all the way to, I'm going to do 50. Okay? And then graph. And for whatever reason, it's not giving me anything. That's weird. Okay, let me go back and check my equation. Oh, the parentheses here, right? So I should... Oh, and I'm missing a T here. Okay, let me... Okay, maybe... Oh, yeah, it's a syntax error. Let me delete this. And let me put the insert. Let me insert a T. All right. There you go. So we'll get to see the graph. All right. Is that correct? T minus 16t squared. Okay, 2.5. Yep, that's supposed to be the one. Okay, let me increase maybe the window for the x because I need to see. Oh, it was supposed to be 400. All right, 450 graph. There you go. All right, maybe 500. Let me change this to 500. Much better. All right. So that is the trajectory of the baseball here. And at x equals to what? 373, 375. There's a 10 feet high fence. The question is it gonna make it or not? All right. Well, so that's the picture. That's the picture of the situation here. Let's well, I'll draw it later. Okay. So here I need to set the x component, the x of t, equals to 375. Why is that? Because that's I need to set when it's the ball going to be 375 feet away from its hitting point, and then I'm gonna find the height at that value of x, and define the y component, and to determine if it's gonna make it or not. That means 140 cosine 22 degrees t, set it equal to 375. That is, t equals to 375 divided by all this 140 cosine 22 degrees. And that's going to be t approximately 2.89. Right? That's approximately 2.889. Okay? So, seconds. And then I'm going to substitute this number in the y component of the vector valued function to find out what's the height at the same time where x equals 375. So let's evaluate y at 2.889, and that equals 2.5 plus 140 sine 22 degrees times the time 2.889 rather, and minus 16 times 2.889 quantity squared. And well, this is going to give us approximately 20.40 feet. So it's going to make it, right? It's going to make it through, it's going to make it past the fence. That means it's going to do something like, if this is 10, right? 10 feet. Twice, so that's going to be something like this, roughly, right? That's what the baseball is doing. So I wanted to wait until the very end to draw the trajectory of the baseball based on our final calculation here. All right? So this is the end of 14.3, right? I believe. Okay.